How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at 14.5 problems. Temperature and rate, objectives, explain the chemical reactions in terms of the collision model, interpret corresponding potential energy diagrams, and use the Arrhenius equation. All right, number one, why does the reaction rate increase as temperature goes up? Well, let's see. Let's work through it. Reactant molecules collide less often? That's not true. Reactant molecules collide more frequently? Yeah. With less energy? No. At higher temperatures, they got more energy, so it can't be that one. Reactant molecules collide more often. That's true. With more energy, that is very true. They're given more energy as temperature goes up. They're moving around faster, which means they got more energy when they do collide, and because they're moving faster, they also collide more often. Well, let's read the rest of them. Reactants collide less frequency. That's not true. I'm not even going to read the rest of it. Activation energy is lower. No, this describes a catalyst, right? Increasing the temperature doesn't change the activation energy, how much energy it takes to start the reaction. It changes how many of those molecules have enough energy. All right, two, in the energy profile of a reaction, the thing that exists at the top of the curve is called the blank. So we have potential energy on one side, and we got time on that, right? So we start at some amount of energy reactant. We add enough energy to get the reaction started. Reaction occurs, and then we're making new products. So it's saying what's right here at the peak. This is what we call the activated complex. So your reactants collide with enough energy in the right orientation for a moment. They've created the activated complex, which means old bonds will break and new ones will be formed. All right. The activation energy is from where you started to where you had to get all the way up there. So this right here is the activation energy. This line right here is the heat of reactants. And this line where you end up is the heat of the products. The difference between the two is your change in heat, the enthalpy of reaction. All right, number three, what is the activation energy for the forward reaction? So we're saying, hey, going left to right, that's the forward reaction. What is the activation energy? It's from where you started to the very peak. So A is going to be your activation energy for the forward reaction. What is the activation energy for the reverse reaction? Well, reverse reaction is we're starting down here, and we got to still go to the very tippy top, to the peak. So let's see, what would that be? It would have to actually be A plus B for that. Yeah. 5, in the Arrhenius equation, K equals capital A, E to the EART, what does A represent? A is the collision factor. Right, we have EA, which is the activation energy. How much energy does it take to get that reaction started? We have R, which is the constant, and T, which is temperature. And A is basically the collision factor. It's accounting for the difference of like, hey, here's one reaction where two things just have to bump in and it doesn't matter, versus another one where it's like, hey, we need three things to come together perfectly in three-dimensional space and collide in the perfect orientation. That's going to change the collision factor. All right, number 6, a first order reaction has a rate constant of this at that temperature. What is the magnitude of K at a new temperature if they give you the activation energy? All right, so long story short, we go, hey, I know the natural log of the amount at some time for a first order reaction equals negative KT plus the natural log of what you started at. I don't know why I drew an A there. So if we were like, hey, that's at a given temperature. All right, at a different temperature, it's the same equation, but the K values are going to be different. Which means that, hey, if I wanted to know what is the new K constant, if I subtracted this equation and started to rearrange and do some stuff, I'm going to get this equation. The natural log of the K constant at 1 um, All right, first order reaction has a rate constant of 2.45 times 10 to the second per second at 35 Celsius. What is the magnitude of K at 85 degrees Celsius if this is the activation energy? All right, long story short, this is going to be an equation that is worth remembering. All right, so when we're comparing rate constants at different temperatures, this is our go-to equation. All right, you can work through it and get it, but let's just maybe put this on the list of ones that we'll just look up or remember. And it's saying, hey, we want to know what is the magnitude of K at a new temperature. Well, let me break this apart. K1 divided by K2 inside a natural log could be expressed as ln of K1 minus ln of K2. And I'm going to say, hey, K1, let's make at 85 degrees, and K2, we're going to make at 35 degrees. And the reason I'm going to do that is because I want to get K1 just by itself, and it's going to be easier to do, right? EA on R times 1 over T2 minus 1 over T1. Now, if I want to get this K1 by itself, I can just add the natural log of K2 to both sides, and that was pretty easy. So now to get rid of this natural log, I got to put the other side to the base, E, Euler's number. So I get K1 equals E to the all that stuff. Now remember the temperatures we got to convert to Kelvin. So 85 Celsius plus 273, is that 358 Kelvin? And then 35 degrees Celsius plus 273 was 308 Kelvin. So this 308 Kelvin is my T2. This 358 is my T1. And let's see, I got 44.5 kilojoules per mole. That's my EA. So I got this. R is a constant. T2, T1. We got all those things. So now I can plug and chug. All right, so let me plug and chug some of these numbers. I got E to the, my activation energy, 44.5 kilojoules per mole, divided by my R constant, which I want to make sure that I keep it in kilojoules. So it's going to be 0.008314 kilojoules per mole Kelvin, times by 1 over T2. And I said my T2 is going to be 308, so 308 Kelvin, minus 1 over my T1, which is my 358 Kelvin. And when I plug and chug, and if I do it all right, I end up with a final answer of 2,770 when I round it to 3 sig figs. Right? The units on that would be to second to the minus 1. All right, that was kind of a rough one for me. I don't know why. Hope you found it helpful and see you in class. Okay, bye.